Hi, steel friends. Today I want to take you through calculating the design strength for a tension member based on the yielding and fracture limit states. Alright, so in this particular example we have two 1/2 by 12 inch plate members. Okay, and they are connected to one another via a splice plate. Two splice plates that are 3/8 inch by 12 inches. Okay, and so we have, if we look at this, right, we have the 1/2 by 12 inch member, and so that's here. And then we have the two splice plates above going here. Okay, and then this 1/2 by 12 inch member over here is separated from this one, and you can see that separation. There's like a little bit of a gap in here, so just make sure we know that this is a hole or a gap. So that's the forces are traveling through the plate, then through the splice plates to the plate on the left. All right, so everything is denoted. The geometry of the connection is given, and we're also told that it's made of A36 steel and 5/8 inch diameter bolts. All right, so I think at the very beginning we need to decide, do we need to design the 1/2 by 12 inch plates, or do we need to design the 3/8 by 12 inch plates? Okay, and so if we take a look, that is our first consideration. So we'll just write that down, that we must consider in our design the tensile strength of both the PL 1/2 by 12 inch member and the PL 3/8 by 12 splice plates. Alright, so again, we kind of rehash these distances. So here in the splice plate, we have 3/8 of an inch and 3/8 of an inch. So the combined thickness of the splice plates is 2 times 3/8 of an inch. And so that is 3/4 of an inch, or 6/8 of an inch. Whereas our PL 1/2 by 12 only has one plate, and so our member is only a 1/2 inch thick. Okay, and so there, very quickly, we can see that the PL 1/2 by 12 member will control our design. All right, so that's the member that we want to design, and so that's the one we're going to check. All right, so we learned in class the two limit states of yielding and fracture for these tension members, and so let's go ahead and work through those. So our first limit state of yielding. For yielding, we said that the design strength, or phi(PN), is going to be phi times Fy times Ag. So we can look up in our manual, phi for yielding in steel is 0.90. Our material property, Fy, for an A36 steel will be 36 KSI. And Ag for the 1/2 by 12 inch member is going to be a 1/2 inch thick times 12 inches wide. So that gives us a total gross area of 6 inches squared. So we can go through our calculations, and we see that phi(PN) totals 0.90 times 36 KSI times 6 inches squared. And so that gives us a total design strength and yielding of 194 kips. All right, that covers our yielding limit state. Now the next limit state we're concerned about is fracture. All right, so I want to return back up to the top here to check out our connection. Now, we talked about in class that yielding, right? Yielding happens in the gross area, so we're concerned about yielding along the entire length of the member, right? So this is where our gross cross-sectional area is. However, fracture, we're concerned about any reductions in the area that we might have, or we're concerned about the material physically breaking along the net section. And so when we talk about the net section, we first think the net section as being the section A, B, C, D, E. Okay, so the fracture will always initiate, or theoretically initiate at the forward edge of the connection. So all this force is in the member, and then it will break along this first bolt line here. All right, so we want to first take a look at along path A, B, C, D, E in terms of our fracture. All right, so we come in and we can set about putting our fracture formula down. So we're looking to design for fracture. So we say that phi Pn is phi times F sub u times our effective area. For a fracture, we use a reduction factor of 0.75. F sub u for an A36 steel is 58 KSI. And if you need to look this up, you want to check out table 2-4, 2-5 in our steel manual. And lastly, we go to chapter D and we can look up the effective area, and we see that the effective area is our net area times U. Okay, and remember, U was that shear lag factor. Now, in this case, U is 1, since all cross-sectional elements are connected. Okay, and so this is case 1 in table D3. All right, so that leaves us just to calculate the net area. Okay, and so we said our net area is our gross cross-sectional area minus now the number of bolts that we pass through. So I'll just say the summation of the number of bolts that we pass through, the diameter of those bolts, plus 1/8 of an inch. Remember, we draw our holes a little bit larger, and we also account for a little bit of damage. So we have to take the diameter and multiply it by the thickness and however many that we go through, okay? And so this is going to be N, or the number of bolts that we pass through. However, when we do staggered connections, we need to look out for the possibility, because if it fails along the stagger, according to our manual, our formula then adds kind of an additional amount for the hypotenuse, and we say that that amount is going to be s squared over 4g times the thickness of the plates. And I'll say here, this is the number of our diagonal paths. All right, so let's go back to our connection. Before I do that, I want to set up a table. So let me set up a table here. And I want to consider different paths. And I want to consider our net area along those paths. All right, so we come back and we first look. We said we guessed path A, B, C, D, E. They're colored in red. And so that'll be the first path we check. So A, B, C, D, E. So we see along that path our gross cross-sectional area is 6 inches squared. This is what we had for yielding. And then as we move across that path, we pass through 3 bolt holes, or we have to subtract out 3 diameters of those bolt holes, which they were 5/8 inch thick. And then we multiply that by the thickness of the plate, which was 1/2 inch. We don't go across any diagonal paths, so that term is 0. And we can come out with our area, and it's going to be 4.875 inches squared. All right, now we're talking about the staggered paths. What do I mean? So we know it can fail straight across, but what if it came down to bolt B and then went off at some sort of diagonal to F, and then it came back to C, and then back to G, and then back to D, and then down to E. Okay, and so that's the next line we want to consider. Remember, this is still the forward edge of the connection. It's just now crossing these diagonals. So if we want to look at now path AB, FCG, DE, we would say that our gross cross-sectional area is 6 inches squared. Now that path along the width passes through 1, 2, 3, 4, 5 bolt holes. So I subtract out 5 times 5/8 inch plus our 1/8 of an inch times a 1/2 inch. However, because that now assumes that all 5 bolt holes are in a line, but since we're sort of on this diagonal here, we need to look at these diagonals. And you can see that this particular path has 4 diagonals. And so that gives us a little bit extra area. And so we have to account for that, adding a 4 times this term s squared over 4g. Now, we can't really derive this term. It came from some tests. But it works pretty well for our bolted connections. And so we just add in this term, 4 of them for 4 diagonals times s squared over 4 times g. And then we multiply by the thickness. Okay, and then just to recap, if you don't remember, S is going to be our stagger. So S is our stagger, and it's going to be 3 inches here. So it's the value here in the longitudinal direction. And then G is our gauge distance, which is along the width of the connection, and G is 2 inches. Okay, so those are those variables for the fracture net area formula. All right, so if we do the math here, I have it calculated out to be a total of 6.375 inches squared. All right, we can continue guessing paths. So the best way is to just guess feasible paths. So what if I tried like A to B, and then I came down to C, and then I could come straight down to D to E. Okay, so now I'm looking at A, B, F, C, D, E. A, B, F, C, D, E. All right, again, 6 inches squared. This path now takes us through only 4 bolt holes along the width. So I subtract out 4 times 5/8 inch plus 1/8 inch times a 1/2 inch thick. And then I have to add the number of diagonals that I went on. I went on 2 diagonals that time. And so then I add in this term, s squared over 4g times our thickness. And so my calculations there give me 5.625 inches squared. Okay, so far, the first path is our critical path because it has the lowest net area. We see that the more staggers we go on, that tends to kind of help it. So, the blue path was slightly higher than our green path. We can keep guessing paths. We can then look at path like A, B, C, G, D, E. But we should be able to notice that A, B, C, G, D, E is pretty much the exact same path as A, B, F, C, D, E. And so even if you want to write it down, A, B, C, G, D, E, we should see that this is the same as the previous A, B, F, C, D, E. And so this will still result in 5.625 inches squared. And so it's still not the critical path for us. Now, we might want to try something completely different. Maybe it will come down and go A to B and then to F. And then it won't go back to C. It'll go to G and then the D and E. So this is, another possible scenario. So we can go through our calculation. So this is now A, B, F, G, D, E. So this is going to be 6 inches squared. It goes through 4 bolt holes across the width. And it goes on 2 diagonals. So already we should be able to see that it's going to have the same net area as the previous 2 that we calculated. However, ABFGDE is not likely to control relative to those 2 previous ones. And that is because if we did a free body diagram of this line, we would see that it only contains now 1, 2, 3, 4, 5, 6, 7 bolts on that free body diagram. And so it is only carrying 7/8 of the total applied load. Okay, and so because this path excludes bolt hole C, it only carries 7/8 of the load. And so what does that mean? Well, that basically in our design equation, we say that P sub U has to be less than phi Pn. But now we're only carrying 7/8 P sub U. So if I want to compare, net areas to each other, I need to kind of keep my load constant. And so therefore I need to bring the 7/8 to the other side, and I'm going to kind of have that then multiply my net area or my effective area here. So I need this 8/7 factor. Okay, so to compare path to path, I'm going to multiply this by 8/7. This will then increase the load and is then not likely to control in my design. Again, I could keep guessing paths, but I think these are the ones that I would first take a look at, and I think it's then most likely that A, B, C, D, E is going to be our controlling path. So we can then finish our fracture calculation. Phi Pn is now 0.75, our phi factor, times F sub u we said was 58 ksi, times A sub E, and then A sub E is our net area. Our lowest net area was path ABCDE, so 4.875 inches squared, times our U of 1. Again, this was our controlling path. If you want to make sure you note that. And so we can do our calculation. Phi Pn for fracture comes out to a total of 212 kips. All right, so we can then work towards our conclusion. For yielding, we calculated our design strength to be 194 kips. For fracture, we got a total design strength of 212 kips. And so we see that yielding in this case controls, and we would report our final design strength that this connection could hold was 194 kips. Now again, we could look at the splice plates, but the splice plates, because the combined thickness is higher, it's going to be not as critical as this 194 kips. So we're going to get all capacities higher than 194 there. It's also very important to mention that this is not all the limit states we must consider. So we will be learning another limit state called block shear. So a complete design check must include block shear, which was not done in this example. And of course, because we have these bolts, we'll have to check various bolt limit states as well for this connection. Okay, but to date, this is what we know. So Based on yielding and fracture, our design strength for this connection would be 194 kips.